strongly correlated systems. Okay, so when we have strongly correlated systems, as you may know from the equilibrium case, we are going to have interactions that are important to describe the physics. So we now are going to have interactions. And the question that remains at this point is if we can take into account both the interactions and the Floquet field together, combine them, and find novel, interesting physics. So far what I told you was how to apply Floquet engineering to band structures, basically, non-interacting models. So what we found in the last lecture is that you can start with some non-interacting model and make it more interesting. So we did this with graphene, it became a churn insulator, and we did it with a 1D model, and it became also the realization of this towless pumping model as well. So today, the question that we are trying to address is if we can also consider interactions and follow more or less the same procedure, or if something changes dramatically. Maybe Floquet engineering is just not useful when you have interactions, but I'm going to try to convince you that with interactions, the situation can become even more interesting. With interactions, there are several phases of matter that we don't understand very well. So I will be using as examples the Hubbard model leading to magnetic models, and in particular, and this follows from yesterday's colloquium as well, by Neto, I will be particularly interested in magnetic models with frustration, okay? This is the number one example that we're going to address, and example number two is to start from an Anderson model, and then at low energies, this is going to become an effective Kondo model. And I want to ask the following question: can I effectively have a multi-channel Kondo model? If you're not familiar with these phases of matter, I will describe them briefly in equilibrium before moving to Floquet engineering, okay? These are two of the most famous and interesting problems in strongly correlated systems. And what we're going to try to do is use Floquet engineering to increase frustration, and I will tell you why, and use Floquet engineering to end up with a multi-channel Kondo model. Why multi-channel, not single channel? I will also tell you why and how. So this is our menu for today and maybe for the beginning of the next lecture, okay? And then tomorrow I will tell you about some very recent advances in Floquet engineering, and then we wrap up. Before going to 1 and 2, that is going to be our main concern here, let me just show you some slides related to questions that you had yesterday, okay? I will just show the references here. So the first reference in Floquet engineering that contributed to make this field of research significantly more productive, and it really exploded, was this pioneer reference here from 2009, the photovoltaic Hall effect in graphene. So this one we already addressed. I showed you it's how to solve graphene in the presence of light, so this is a pioneering work. I will list all the references for you. I put the website here. I will list all of them in that particular website, but I'm just showing because it's not listed yet. I will be doing that in the next few days. So please, if you are curious about these references, go back to the website tomorrow or over the weekend. I'll be wrapping up the website as well, including notes and links to videos and references and slides. But just to give some credits at this point, the graphene work, the pioneer work, is this one from 2009 by Oka and Aoki. I had a question yesterday about how to classify topological insulators after we do the Floquet engineering. So this is the work that did that, the periodic table for Floquet topological insulators following the 10 Outland Zirnbauer symmetry classes, and how do you do this for Floquet. I will also include this reference there in our webpage, but since we got a specific question about this, I would suggest this reference from 2017. Finally, the two works related to bicircular light that we also addressed yesterday, I would suggest these two. So at least the lectures were based on these two models, or these two papers. The first from 2019 and then from 2022. The first one has interacting electron systems. What I did was the non-interacting case, adding interactions. What was done in this paper, it's one example of what we're going to address during this lecture, but even the non-interacting case is nicely worked out in this reference here from 2019. Okay, and also to give some credit, yesterday I put this model for the 1D chain with this delta 1 and delta 2, so this was the second half of the lecture, and this model was first proposed in this particular paper here, okay, by Rice and Mel from '82, that time-dependent model in the context of diatomic chains. So if you have two inequivalent atoms per unit cell and you drive it, I would suggest you reading this from '82. This was done before all this technology, or before this new way of looking at the problem with Floquet engineering, but the problem is posted in this particular paper from 1982. Okay, just some references. These are some papers that you can consult, but again, I will put these slides, I will upload the slides to the website, to my personal website, and I will also include all these references in a single file, like the links to the references. This will be done tomorrow, over the weekend, or early next week. I expect this to converge, okay? All right, so now let's talk about this, the possibility of including interactions to Floquet systems. Does anybody have any questions so far about what I showed, references or anything in general before we move on? Okay, good. So let's now include interactions, and let's start from one. So Hubbard models leading to spin models. We have to do this before including the Floquet field, the same way as we solved graphene before including the Floquet field. This problem is significantly harder to solve, as it is often the case when you include strong interactions, or interactions that cannot be easily neglected. Okay, so I will write down the Hamiltonian as our starting point. I will write minus TH, sum over J and sigma, C, J sigma. And then you can do this in 1D or in any dimension. Let me do it generically like this. C I dagger Cj. You can have Hermitian conjugate. I will assume that this term is Hermitian. Plus U sum over J and J up and J down. So these are spinful electrons. And again, this is going to destroy an electron with spin sigma. So this is a spin index. There's a spin index. And it's going to destroy an electron with spin sigma from one point of your lattice and create some place cells. And I and J are such that this Hamiltonian is Hermitian. It has a single hopping parameter. That's okay. And now we add this Coulomb term. This is a Coulomb repulsion term. So Coulomb repulsion term. And I will assume that U is a positive number. So if U is a positive number, you have a price to pay if you put two electrons at the same site. So far you can think of some lattice, some general lattice, let's say like this. And in general lattice, you have the sites. So each point here is a site. And if you try to put a single electron, you're fine. You don't pay this. Notice that to pay U, you need an electron with spin up and an electron with spin down at the same site. So if that particular site has only one electron or 0 electrons, you don't pay U. There is also a chemical potential term. So I'm not writing down the chemical potential term that is going to control the occupation. So you have to set up what is your chemical potential to know what is the number of electrons that you're going to have. And in today's lecture, I'll be interested in the limit of half-filling. Half-filling means that the number of electrons is equal to, in this case, the number of atoms here. So let's say that, or number of sites. So half-filling is, on average, one electron per site. Okay, one electron per site. This model is already quite interesting even before we do anything else. I will be considering a limit here. So this, again, is a very rich model. You can dedicate decades of your time to study all the different possible behaviors that these models like this can have. But I'll be interested in one particular limit in which U is much larger than TH. Okay? This is the relevant limit today. It's not the only possibility. You can set U to 0. You are back to last lecture in which you only have hoppings around this lattice. And you can set TH to 0. And then you are back to a model in which the electrons don't move at all. They just sit some particular sites. No, these operators are acting on sites. So if I label this site as I, and if I label this site as J, so this term here is destroying one electron from J and moving it to I. It's doing something like this. So these are defined in real space. Of course, if you don't have U, you can easily go to momentum space. It's a much better basis. But for today's lecture, in this limit, in which U is much larger than TH, it's better to work in real space. Okay? All right, so if you have the chemical potential such that you have, on average, one electron per site, and if U is much larger than T, the ground state configuration of this model is quite simple to guess. Okay? You just populate all sites with a single electron. So all sites are going to have one single electron. All right, but you can ask me, well, each site has one electron, but electrons have spins. Is the spin pointing up or is the spin pointing down? It doesn't really matter. So in each site, the spin can either point up or down. And these two states have the same energy. In the limit in which U, you take U to infinity, basically, by making it extremely larger than TH. In this limit, if you just neglect this term, this is the first approximation as usual. This week we did a lot of perturbation theory, and this is going to be, again, a perturbative argument. If U is much larger than TH, let's start by solving the model with U, with TH equals 0, so just U. So in this limit of just U, if I have half-filling, I don't want to pay U for any particular site. I want to have the ground state such that I don't pay U. And the way of not paying U is by having one electron per site, either with spin up or spin down. Okay? So this is the ground state configuration when TH goes to 0, or more precisely, when U divided by TH goes to infinity. Okay? So we have a dimensionless parameter here that is going to control our physics, U by TH. So this is, again, when TH goes to 0, this is the ground state. One electron in each site, they don't move around. It is what it is. If you bringing back TH by U finite, which means that this number is now non-zero, so TH finite but much smaller than 1, we can do perturbation theory, and this is a massively degenerate ground state. So in each site, you can have spin pointing up, or the electron with spin pointing up or down. On each site. This is on each site. So this is a degenerate state, completely degenerate state, the degeneracy is 2 to the power n, where n is the number of sites, okay? As opposed to 4 to the power n, which is the total number of states. Your Fock space has 4 to the power n states, because on each site you may have 0 electrons, 1 electron with spin up, 1 electron with spin down, or 2 electrons. So you have 4 states in total, but this ground state configuration is still massively degenerate, so it's 2 to the power n, but this is much, much smaller than what you had before. Before you had 4 to the power n. And now we want to treat this problem perturbatively. There are many, many ways of doing this. This is one of the most elementary calculations that you can do when you are studying correlated systems. You choose the way you prefer. One possible way is that you put sites I and j here, and then you just solve for this molecule. You solve this molecule problem exactly. So you put this TH here of this molecule, and then you put the Hubbard U here, and the Hubbard U here. You solve this problem. It has a total of 16 states, 4 states from here, 4 states from here, and then you take the limit in which TH by U is significantly smaller than 1, and you look at the states. You look at the states. This is one possible way of doing this. I find this to be very effective. You can also do this degenerate perturbation theory. And you have to go to second order in degenerate perturbation theory. And you're going to, of course, have the same result. And the result is the following. You're going to find at low energies, an effective Hamiltonian in which the charges' degrees of freedom are frozen. It's pricey to move from one side to the other directly, like this. You're going to pay the Hubbard U. We call this term the Hubbard U. And you don't want to pay the Hubbard U. So these processes are only allowed virtually, as it is often the case in perturbation theory. So at low energies, you end up with an effective model, H effective, that I won't have time to derive this at all. It will be 40 minutes or 20 minutes of this derivation, but if in case you have never seen this before, it's a very nice first exercise to do. Solve this molecule, 16 states, it's a 16 by 16 matrix, make it block diagonal, expand the eigenvalues, you can find all eigenvalues exactly, all eigenstates exactly. It's a nice problem to solve as a warm-up. 4t h squared divided by u, sum over, now I will put only nearest neighbors, okay? I will assume that I and j, this is only non-zero if I and j, let's say, are nearest neighbors, what is represented by this symbol here, okay? Sum over I and j, si dot sj, okay? Si dot sj. The idea is that if you have two sites and you put one electron here and one electron there, you can move this guy to here and then move this guy back virtually. And this leads to an effective spin-spin interaction between these two sites, so site I and site J. They were initially occupied by one electron each. Let's say that this electron had a spin up and this had a spin down. If they both have spins up, you cannot move this guy to here because of the Pauli exclusion principle. This is not allowed. But if they have opposite spins, you can move this guy here, it becomes doubly occupied, and then you move the other guy to here. This is the virtual process that will lead to this effective Hamiltonian in perturbation theory. So you can do this approach or the molecule approach. Both of them are going to lead to this remarkable result, that at low energies, a model which has charge and electron degrees of freedom will have the charge degree of freedom frozen, and the effective interaction is a spin-spin interaction. Okay? Yeah, for this one, from now on, this is general, but let's assume for concreteness that this is only non-zero. Here I was being very general, but now since we're putting a lattice, let's assume that only nearest neighbors can hop, okay? It's completely possible to put next nearest neighbor hoppings, let's say along this diagonal. It'll be here for the square lattice, along the diagonal. Typically, this is, I will just put a bracket here what these things are called. So nearest neighbors are typically called T, these hoppings, but we cannot use T here for obvious reasons. We have time. And the other ones are T2, T3, and so on. This is nearest neighbor, this is next nearest neighbor, and so on. Typically, in materials, T2 is significantly smaller than T1, T3 is significantly smaller than, let's call this T1 for, just to avoid problems with time, okay? With the time variable. No, if you have T, what is always true is that you can solve for a molecule, but now you can solve for these two together coupled by T2 directly. And now it will have an effective coupling. If you have T2, you already get. So this is an important question, actually. So this is going to be a nearest neighbor spin interaction with an exchange coupling that I'm going to call J, already knowing that from the previous lectures you wrote J several times for something else, but it is what it is. I mean, the J's from the previous lectures is not at all the J from this lecture. In fact, the J from previous lectures is what is TH here, but it's conventional to call this spin-spin interaction by J. You can call it J exchange if you will, but I will probably drop this. 4TH squared divided by U, okay? Nearest neighbor, antiferromagnetic spin interaction. As Pedro was asking, if you consider T2, you already gain directly a next nearest neighbor interaction, which is called J2, which is going to be 4T2 squared by U. This comes for free because you solve that molecule. But since we have this question about the next nearest neighbors, in higher orders in perturbation theory, so this is if you have T2 finite, but even if you don't, higher orders in perturbation theory will give you a J2. So this will be, we are going to set this to 0 probably in today's entire lecture because we are going to assume that T2 is 0. But in higher orders in perturbation theory, you get 4 TH by U to the power 3. So if you go to higher orders in perturbation theory, higher orders, you can start from here. The electron can hop via T1 here, and then it hops again. So that's already T1, and then back, and then back. Okay, so that requires 4 factors of what I'm calling TH here. T1, I will make it very clear here that what I initially called TH is now T1, since we had the question, okay? The hopping, nearest neighbor hopping. But with enough orders in perturbation theory, or very high orders in perturbation theory, you can go to any other place and come back. But recall that we are under the assumption that this T by U is much smaller than 1, okay? This is our working assumption. This is our working assumption. Okay? And while this number 4 is the same for all lattices, this number here, exchange 4TH, is the same for all lattices, because it's just a two-side problem. It's a two-side problem. It doesn't mean that if it's, this could be a Kagome lattice, this could be a honeycomb, a square, triangular, all lattices, since we are solving for two sides, this term here will be always like this. But corrections of higher order will not necessarily be the same, okay? Notice that the geometry of the lattice is very important. In particular, you have to start counting possible paths. And this is time-consuming. It's straightforward and time-consuming, because now I chose one particular path here, but you could, instead of choosing this path, you could have chosen this path here. Okay, you go, and then you come back. And these two paths contribute to the same interaction. And you have to add them up. So at some point, this number here, the numbers of higher order, they have to do with the geometry of your lattice. Unlike this 4 here, that it's a two-side problem only. Okay, but so far we found an effective spin model, and we are almost ready to start discussing the Floquet engineering of this model, okay? So as presented in yesterday's colloquium and as typically discussed in this field of strongly correlated systems, we want to know what are the possible phases coming from this spin model, okay? What are the possible phases? If you go to a triangular, if you go to the honeycomb, not the honeycomb, sorry, square lattice. If you go to the square lattice, if this exchange is positive, as it is the case here, so this model, this Hubbard model, leads naturally to an exchange coupling which is positive. The ground state, as discussed in yesterday's colloquium, is going to be a state like this, okay? State like this, in which you can minimize the energy by making the spins point, nearest neighbor spins pointing in opposite directions, okay? All of them in opposite directions. This is not an eigenstate of the quantum Hamiltonian, but the order remains. Even though this is, if you write down this state and apply the Hamiltonian, it's not an eigenstate, but this order is there. The antiferromagnetic, it's called antiferromagnetic order. Antiferromagnetic order, okay? And again, using yesterday's colloquium, I can tell you that something that you can do this phase is interesting, of course. Unlike magnets that were understood and seen in nature for many, many centuries, phases like this were not so well understood until quantum mechanics appeared and we started looking for other possibilities. This phase has zero magnetization. Okay, that's why it's more subtle from the point of view of finding it in nature naturally. But it's still interesting, but well understood. So what would we like to do? We would like to take this state, this order corresponding to this particular type of state, and make it melt. So we want to. This is a state that we want to destroy. Why would we want to destroy this state? Because we want to find even more exotic phases of matter. And in particular, just for concreteness, you can choose your favorite phase of matter and ask the following question. How can I Floquet engineer a system such that I can produce this particular phase of matter? And in today's talk, or in today's lecture, I want to find spin liquids. Spin liquids. How? I will tell just a few words about spin liquids. Again, yesterday I didn't tell you much about how to compute topological indices, and today I will not tell you much about how to solve spin liquid problems, but I want to tell you how to produce, how to engineer a spin liquid Hamiltonian. Spin liquids were first proposed by Phil Anderson in 1973. It's an extremely entangled phase of matter. Until recently, 20 years ago, there was no model that could be exactly solved producing a spin liquid in 2 or higher dimensions. Now we know models that are exactly solvable and present spin liquid physics. But still, it's challenging to describe these phases and harder to access experimentally. So it looks like a great idea to Floquet engineer a model, and today I will Floquet engineer this model, trying to produce a phase like this. In general, if you want to produce phases that are highly entangled and so on, a good idea is to start with frustration. Okay? How to generate frustration in this model? Well, you just try to make these 2 spins connected by J2. Again, it's the same as the colloquium yesterday, so I'm recapping for concreteness. Okay, so you have J2 here, and so on. If J2 is positive, spin up and spin up, this is not a very happy situation because this costs energy. So it's not a good idea to have J2 comparable to J1 and think of this state here. Maybe there is something better that can be done. And again, these are all of these models, let me emphasize, these are spin half models, okay? This is spin half models, extremely quantum, okay? Spin half quantum models. Okay, so But I already told there was a question about this, that I can have, sure, nearest next neighbors appearing, but this is very high order in perturbation theory, okay? In particular, if you take the ratio of this, let's call this J exchange now J1. If I take the ratio, T2 is not going to help you much. T1 is typically smaller, oh, sorry, much larger than T2. So this term is not going to do much. But now if I take this ratio of J2 by J1, you'll see that it's also significantly smaller than 1 by 2 orders, by 2 orders in perturbation theory. So this goes as TH by U to the power 2, which is significantly smaller than 1. So this model is not doing the job. This model is not doing the job of producing possibly spin liquid phases. Yes, there is a J2, but not a J2 that is significant enough to melt this phase. But how do I know that? In principle, for this mini course, you don't know that. You have to, by numerical simulations, most likely, combined with analytical tools, try to solve this problem with J1 and J2 and see, as a function of J2 by J1, where the state melts. So there is probably a number here, so this is an antiferrole, and then it transitions to something else. Typically here in the middle, so there is also the limit, so let's say 0 here, and let's put infinite here. Typically in the middle here is where you get the most interesting features. Okay? As it is often the case in these strongly correlated systems, is when you have 2 scales, J2 and J1, and I cannot easily neglect either of them, or neither of them. J2 has to be considered, J1 has to be considered. Okay? And again, I will not find these phase diagrams. It's not the point of this mini course. It's done mostly by numerical simulations. I will show you in a moment some phase diagrams obtained numerically. But what I would like to engineer is a way of making J2 larger and J1 smaller. So how to make, so the question is how to make J2 by J1 larger. Okay? You can always argue that this model is too simple and so on and doesn't really capture more sophisticated materials and so on. Okay, but let's assume that this is the starting model, and within this approximation, try to make this ratio larger. Okay? At this point, you probably guessed how we are going to do this. We are going to do this by Floquet engineering, of course. By Floquet engineering. The idea is, from now on, the same as yesterday. The question is the questions are, does it work? And how does it work? So let's see. We are going to take our lattice, assuming the lattice to be 2D again. Assuming the lattice to be 2D, we're going to shine light, or we're going to make the problem time periodic, and ask what are the effective interactions that we get. And the answer is kind of already here. We spent 3 lectures learning all that we could about how to make this problem time dependent. So what is going to happen if you couple with lights is that the hopping term will acquire a Parrot's phase, the same as we did yesterday. And this term here, recall that Nj of sigma is Cj sigma dagger, Cj sigma. So it's a number operator. These number operators are both at the same site. And they have the dagger and the not dagger. These guys don't acquire a Parrot's phase, okay? Because if you think of this guy, it's the line integral from J to J, okay? So the number operators are all at site J. There's no phase. So Parrot's substitution for this, no substitution for it, it remains the same. The chemical potential also remains the same. So there is a chemical potential term. So let me write it down. It's minus mu sum over I and sigma, or J and sigma, and J sigma. The chemical potential term also does not change. So the only thing that will change is the hopping. And we are going to have the diagonal terms in our Floquet Hamiltonian, the different photon sectors. Okay? Questions so far? No questions? Okay. So this is our prescription. This prescription can be done to any lattice. I will just, the most famous one, and Floquet engineering was explored for all of them. I would say the square lattice can be done, the square lattice. The triangular lattice. Just to give some examples. The honeycomb, and also the Kagome lattice. The Kagome was done first. I will not draw the Kagome lattice here. It's slightly more challenging to draw, but if you draw just a tiny piece of it, it looks something like this. Okay, so you have triangles here, and you have this honeycombs here. This lattice is extremely frustrated, intrinsically frustrated, okay? The square lattice, if you only have J1, you can make everybody happy by choosing this configuration, at least classically. The Kagome is not like this. The Kagome, just like the triangular lattice, if you try to make everybody happy, you're going to fail. So if you have a triangle here, and a triangle here, and so on, if you try to play the same game as played here, with spins up and spins down, you're going to fail. You put a spin up here, you put then a spin down here, and then I spin down here, but there's no happiness at this particular bond. The triangular lattice, you can still solve the problem by, these are called Heisenberg spins, okay? They can point in any direction in spin space. So you can try to make everybody as happy as possible by putting relative angles here. You can solve this problem classically first to see what are the angles. You can tilt them a little bit. And then you can still make a state that is magnetically ordered. It's just not going to be up and down like this. The Kagome, you cannot. The Kagome is too frustrated. The level of unhappiness is significantly larger. So quantum mechanically, you're not going to be able to stabilize any phase magnetically ordered when the couplings are positive. It's going to be already a spin liquid state. What do we call a spin liquid? The Kagome lattice. Antiferromagnetic Kagome lattice, even if you don't have any other couplings, next nearest neighbor couplings and so on, so even with only J1, it's already a spin liquid state. But then, of course, with Floquet engineering, spin liquid is not only one possible state. You have different flavors of spin liquids, okay? And maybe if you apply circularly polarized light here, you can maybe even transition from one spin liquid state to another, right? Because for now, we don't have any chirality. But recall what we did for graphene yesterday. We included a magnetic field or an electromagnetic field, and the electrons became chiral. Can we make a spin liquid chiral? The answer is yes. How? By Floquet engineering. The answer is yes. You can do this by Floquet engineering and transition from the Kagome lattice from a spin liquid that is not chiral to a spin liquid that is chiral. Okay, I will show, the next slide will have a plot when this was done, I think in 2019. And I will show you the plot with the two phases. The same way as in graphene, we could measure the chirality by using these Chern numbers. Here there is a very specific thing that you can measure, that is the chirality of each plaquette. So you have plaquettes here, and then you can measure, according to the spin configurations, what is the chirality of a plaquette. It has to do with the cross product and so on of these spin operators. I will show you a slide in a moment. But for the Kagome, the situation is this. We already had a spin liquid, and then you can, in principle, transition to other spin liquids. Here, the challenge is to increase J2 by J1. So just to put the Kagome, for the Kagome, I would say the first thing would be to use chiral light or circularly polarized light and transition from a spin liquid that is not chiral to a spin liquid, to a chiral spin liquid, okay? This would be already pretty cool, and this was done. For the other ones, other lattices, I would say the main priority is to destroy the ordered state, ordered in the sense of, in this sense of having some type of simple Landau-like order parameter. Destroy the, I don't want to say the boring phases, but the well understood phases, the well understood phases, okay? That is our main goal. All of this can be done, and most of this was done in the last 10 years, a bit later than what we discussed last lecture. It's more involving. The calculations don't become any easier if you put strong correlations, but this was done over the past decade or so. Questions? Very good. Just out of curiosity, when we are following this procedure, we are going to be generating a bunch of new couplings. So I'll just list what are the couplings for the triangular case. The triangular, as I told you, from these lattices here, the Kagome is already almost solved in the sense that it presents a spin liquid state even when the other couplings are zero. But for these left three lattices, the easiest one to destabilize is the triangular lattice. It's more frustrated than the square and the honeycomb. Just for concreteness, I will tell you for the triangular lattice, what are the couplings in equilibrium? Okay, in equilibrium, and I can put the references. This is the first lecture about something that I worked on. So I had to do calculations for these lattices and so on. And I can put some references of ways of doing very high orders in perturbation theory for this particular problem efficiently. Otherwise, you'll get completely lost. So for the triangular lattice, you have the triangles like this. J1 is 4t squared by u minus 28 th to the power 4 by u cubed. And again, this number here is lattice dependent. You can have a J2. I will define each number in a moment. 4th squared to the fourth, divided by u cubed. You also have a J3 that is 4th to the power 4 divided by u cubed. And you have something that is a ring exchange term. Ring, which is 80th to the power 4 divided by e cubed, okay? The terms start to proliferate easily, or quickly, if you go to higher orders in perturbation theory, okay? So just to give you a flavor, and all of them are necessary if you want to do the Floquet engineering that I will tell you next. Of course, we're not going to do the algebra for this problem in the presence of Floquet fields. I'm not going to do the algebra even without the Floquet field. I will not derive this number 80 here in front of this. It requires lots of counting. Okay, J1 is just this. J2 is this. J3 is along a line. So J3 is this. And the ring involves a particular configuration of a square. I will not discuss this ring exchange term a lot, but it does also lead to interesting physics. So it has to do with a particular four-body interaction on a particular square. So it's this square can have this, and this spin, all of them interacting. So it's a quite peculiar term. Okay, it has dot products of this and this, this and this, this and this, this and so on. This is called a ring term. The square lattice also has all this coupling, so this is just, I would say this is an example, but it's the most interesting example. This is the triangular lattice. Okay, all right. So what is next now? So now we are going to put the Floquet field. And again, I'm going very slowly because this is the part that I can actually tell you in details about. The Floquet, the calculation with the Floquet fields, we cannot do it. We cannot do this calculation easily on the board, especially. The expressions are pretty lengthy. But we know what are the rules of the game. The rule is that th goes to th e to the minus I line integral from Ri to Rj ADL. ADL, okay? This is the rule of the game. The other terms don't get changed, so let me write just once for any lattice what is the Hamiltonian that we are trying to solve. It's sum over, let's say that I just put nearest neighbors. E to the minus I line integral from Ri to Rj A dl Ci dagger Cj, it's intrinsically Hermitian, plus nothing much here happening. J, Ni up, Ni down, minus the chemical potential term, sum over J and sum over sigma. Okay, J, so this is J and this is J. Very good. Ni, Nj, sigma. That's it. So only this term gets modified. You're going to get Bessel functions just as yesterday. So if you appreciate the Bessel functions yesterday, you're going to appreciate them today, and vice versa. Okay. Why? Oh, this one. Oh, sorry, there is a sum over sigma. I don't know if I put this before, actually, but please correct. All the sums of hopping terms have the sigma sum. Yes, thank you. You can find the Floquet. So now you're going to take this Hamiltonian and find the good old HM. HM. You can do this. Bessel functions and so on. The question that remains to be answered, that is the only question I would say that remains to be answered, is how to solve this problem after you do this. Well, as we learned this week extensively, perturbation theory. Okay, perturbation theory. So I'm back to the Hubbard model. I don't even have a spin model anymore. So my expectation of solving this problem is significantly smaller than my expectation of solving the time-independent problem. And my expectation of solving this time-independent problem was 0. So we're not going to be able to solve it. So let's do perturbation theory. Here, it's not obvious at all. No. Not obvious at all. No. I first calculated these numbers and I was asking this type of question until I found this reference that gave me some light. It's by Ella McDonald and collaborators, in which they table all of this. Then it gave me more confidence. But it does not have to be like this. On a square lattice, J3 is not even along this particular line. You can have other things. So the question is, why is this number equal to this number, right? It's also equal to this number, but yeah. The prefactors require counting. There is no way to know. Okay, so we have the parallel substitution. It's looking good. But we want to do perturbation theory. And the question is, what is the small parameter to do perturbation theory? Okay, what is the small parameter? Well, before it was, so before, we had our TH by U. But now we have light. And light brings our knobs. What are our knobs? We have, and again, I will not redo everything. It's light perpendicular to the plane, and it has some amplitude A0 or fluency A0. It has frequency omega and so on. So these are our parameters. Our polarization, that I always like to emphasize, it's an important parameter, even though it's not a number that appears in our calculation. Our frequency omega and our fluency A0. This is what we have to choose. So we have two new features here. The hoppings will become Bessel functions, as was the case before. So TH will go to this TH, some Bessel functions of order M of A0 times phases. I will not do the algebra, but to lowest order in perturbation theories, these phases will cancel out. Because to lowest order in perturbation theory, you go and then you come back. And you acquire opposite phases when you do that. It's not the case if you go to higher orders. If you can start walking around, then you can gather all types of phases here. This is also interesting. The same way as with graphene yesterday, we had this this K effective that had very peculiar phases. It's the same here. They will not cancel out in higher orders in perturbation theory. But the question that I have to address is, what is the relation between U and omega? That's the concern here. And I will say that they are comparable, but not quite equal. So the perturbation theory is going to be a little bit more complicated now, because I want to find an effective model that has these two features. I want an effective model I want to find an effective model that is a spin model, a spin half model. That is a spin half model, in which I'm integrating out, or, okay, to the lack of a better word, let me say integrating out or summing over, or the way you want to, this is just jargon, I'm not going to be performing any integration. Integrating out high energy degrees of freedom, okay, high energy degrees of freedom. So I don't want double occupancy. Double occupancy is not allowed, not allowed. Empty sites, not allowed. And all the Floquet sectors, so I want to stay zero Floquet sector. This is what is allowed. Other Floquet sectors, not allowed. Until yesterday, this is what we did. We integrate out other sectors and found an effective model. That's why we had this famous sum over M, 1 by omega, 2 omega M, and our commutator here. You may recall. This is this part here. But now I want to combine this with what I did the first half of the lecture. That was to integrate out over double occupancy or zero occupancy. I have to do these two things combined. This can be done. It's degenerate perturbation theory combined with degenerate perturbation theory. So it's going to be a massively degenerate perturbation theory. You can do it. I will just represent schematically what you're doing in this particular case, okay? So schematically, the following thing is happening. You start with, as before, let's see. You start with a spin up and a spin down, let's say. So spin up and spin down. And everything is fine, so let me put here what are the Floquet sector. So you are, let's say, in the m equal to 0 Floquet sector. Everything is fine. Okay? So far, so good. Nothing much. Now you want the electron to hop. So this electron hops, so it's up and down. Very good. But you cannot hop just like this. Recall, every time that you hop, you absorb photons virtually. So you change your Floquet sector. And here, for concreteness, I will say that you are now, so you are here. And now I will say that you are at this m equals -1. Just to, this is the process that happens when m is equal to 1. And then you come back. So this spin comes back, like this, and you're back to the m equals to 0 sector. M equals to 0 sector. So that's also good. So you go, you absorb some photons, and then you remit them. Okay, so the intermediate states, here you're going to pay U. There's no question about it. There's no question about it. You have to pay U. This is a virtual state that is going to cost you U. But you can make your life slightly better. You don't have to pay all this energy by yourself. What you can do is now you can absorb photons. So it's going to be U, let's say minus or plus, depending on how you define this, minus m omega. This can be a great deal. Great deal. You absorb photons to help you pay. It's like a loan. You take a loan to help you pay the Coulomb energy scale. Of course, this loan cannot be so great, because if you can make this 0, well, the electron may just not come back. The electron, well, if this costs 0, why not just stay here? Okay? Free housing. Why not? Well, but then you don't have a spin half model anymore. Okay? Then the charge is moving. You don't have a spin model. So you want to decrease your cost, but you don't want it to decrease by that much. So U minus omega are called resonances. These are resonances. These are cases in which you can move around and not pay any energy. You don't want that. So you want this number to be smaller for all m. That's important, for all m. We're going to see that this is summed over m. So if there is a single m that makes this energy cost to be equal to 0, you're done. You're done in a not so good way, in a bad way, in the sense that you're not going to find an effective spin model. Okay? Exactly. Oh, sorry, yes, precisely. You, exactly. Yeah, I was missing equal to 0. Thank you, yes, these are the resonances. Okay, very good. So you don't want that. You want to do it safely. But doing it safely in this particular case is harder to be sure if you're doing it safely. So it's always good to complement this part with some numerical simulation that would do the exact time evolution of your system. This is always preferable, because how safe can you do this, okay? It's always preferable. I will not write down all the couplings, the effective couplings that are found by doing this procedure. I will just write one of them, the simplest possible one, okay? M is always an integer, yes. Yes. That's precisely the point, yes. So just to repeat the question, if these are the resonances, well, m is an integer. It's not that m is a real number. If I could choose m, if these m's were all the possible real numbers, this condition would always be satisfied. Let's say if I had an integral over m, but m is a set of integers. So I can just choose this ratio, u by omega, let's say far from integers. Yes, that is the basic idea. This is what we want to do. But we also want the couplings to change a little bit, right? Otherwise, this is useless. So it's a tricky game to play. Let me just tell you, so the J1 value let's say J1 with Floquet, divided by the J1 in equilibrium, let's say stationary, as we were saying yesterday, it's going to be a sum over. So if you do, it's the same. This is this result that I'm going to write here is quite simple to derive. I suggest you to try to derive that. This is 4t h squared sum over L, let's say, JL of A0 squared. So this is for circularly polarized light, okay? This is what I'm going to write here. Divided by what? Divided by U minus L omega. L is the same as the M here, okay? I'm just summing over. I always prefer, since this denominator is dimension full and so on, actually, not quite there yet. Okay, this is what it is. So I always prefer to divide this by the stationary number, okay? So Floquet divided by J1 stationary. 4t squared by U is the J stationary, so this is a sum over L, JL of A0 squared divided by 1 minus L omega by U, and I typically call U omega by U omega tilde. Okay, so let me just call it omega tilde. Okay, under the assumption, same assumption as before, that this is as far as possible from 1, or from 1 by L. Okay. All right. But all the other couplings are going to change. All the other couplings are going to change in a way that the expressions become very lengthy. As I told you, to derive this, you already have to do some algebra. The algebra for the Floquet case is not so different as compared to the algebra for this case, except that many things that are summing or canceling out will not do that anymore, and the reason is because of phases. The phases are the novel thing. What if you put linear polarization? Then you don't get as many phases. Well, but then you have other issues. If you put linearly polarized light in some particular direction here, so this is linear polarization, the symmetry of the lattice is destroyed, and then you have to redo the calculations taking that into account. Spin liquids are not going to like lattices that are not symmetric, because then you can find interesting states, magnetically ordered states possibly, that can solve this problem, okay? Again, you can, if you have this lattice and you want to make it very anisotropic, you can shine the light. Let's say one possibility would be like this. This is called, this is linear polarization, horizontally polarized light along this horizontal direction, and then for sure this hoppings or these exchange couplings will be different as compared to the other ones here. But then you can probably find a state of matter that is magnetically ordered that is going to be the ground state of this problem. So the spin liquid state doesn't like breaking symmetries that much. Circularly polarized light is okay, it breaks the mirrors, as I told you, and it's also going to break time reversal. Time reversal is acceptable. To break time reversal in a spin liquid is something that we can accept. Okay. So to wrap up this part of our first correlated model, which is the Hubbard model and how it leads to these phases, I will just show a slide to you which summarizes this. Okay, so this is the good old Kagome lattice, as I told you before. Okay, so the Kagome lattice already has a spin liquid phase as the ground state. So this, sorry, was done in 17. I told you in 19. This was done in 2017, 16 and 17, and so the Kagome lattice is already having the spins here, but they form a spin liquid, and this is the interesting phase diagram. So this phase diagram shows us that as we increase our vector potential, that I'm calling A0 during this lecture. So I changed this. And also as a function of frequency. Again, let's try to avoid resonances, okay? You can go from one phase in which this is called the Z2 phase, what I mentioned before as a spin liquid state that does not break time reversal symmetry, to this state here represented in orange, which is also a spin liquid state. So it's a highly entangled, non-trivial phase of matter with topological order, non-local order parameter, not without any local order parameter, and so on. And from here to here, you acquire chirality. This is circularly polarized light, and this is the way to measure the chirality of the spins. It's the it's around. You go around here in the triangular lattice around one triangle. So one triangle is going to have 3 spins. You collect these 3 spins, and you compute this cross product of 2 of them, and then you dot with the 3rd one. You can convince yourself that this is the chirality on a lattice. Okay. So this phase of matter here, without Floquet engineering and without our great friend, circularly polarized light, would not be simple to engineer. You could try, as some students asked me during the coffee break, wouldn't it be possible just putting a magnetic field? Yes, but a magnetic field will have Zeeman terms that will tend to order magnetically. This is not what we want, okay? This is not what we want. Every time that you're playing this game of Floquet engineering, it's always good to have a phase diagram in equilibrium so you can compare. And this is the case for the triangular lattice. So this is this paper from 2016, in which they computed the entire phase diagram, or this phase diagram, as function of this chiral coupling. The chiral coupling is represented here, so it's the chirality of a triangle. So again, for the triangular lattice, I didn't write here. There is a chiral term that I didn't write just because it's 0 here. So there is a j chi that is 0 to all orders in perturbation theory. In the equilibrium case, you don't have chirality. But as you start adding the Floquet engineering, you calculate this again, and you already get a term that is finite. This is going to become finite naturally. You just redo the calculation in perturbation theory. The phases that I told you about are not going to cancel out anymore. They would cancel in that particular case. And then you end up with some chiral couplings that are finite. So, okay, so we now have chiral couplings. We didn't have that. Now we have chiral couplings, and we have J2, and you can walk around this phase diagram. So the 120 Néel phase is here, represented in orange. It survives for some couplings, for some J-Chis, but then the idea is to transition to a chiral spin liquid here. And here in green is the Z2 spin liquid, and then you have some ordered phases here. Again, this middle of the road here is typically the most interesting part. This is the one that we don't have easy access analytically, but numerically you can find these spin liquid phases, and with the Floquet, you can in principle increase this J chi and increase this J2. Tomorrow, I can show you some plots of these ratios. Okay, I can start the lecture by showing the ratios J chi and J1 and J2 and so on. This is the result of this calculation. But so far, I already showed you for at least the Kagome lattice something that is even more convincing, I would say, than just finding these effective couplings. This was done. You can complement this diagram with what we did here. But this was actually done simulating the Hubbard model, the time-dependent Hubbard model. Okay, so you go back to the first equation that we had, and you simulate it. You simulate it. And then you see if you get this chirality. You can measure the spin chirality. Our approach here is complementary, more. We use most analytical tools. It complements this phase diagram, okay? So by finding effective couplings that are time independent and so on. But the last word comes from time simulations, including simulations in time, like this. This is convincing evidence that a chirality was transferred from the light to the effective spin model, okay? Questions? Unless you find some other way to generate chirality. So the Hubbard model that I showed you had J chi. This model, if you construct only this model, it's J chi equals to 0. So you're already along the x-axis. So nothing can be accessed like this. But additionally, as I showed initially, you also have this J2, and here it should be J chi and J2 divided by J1. So this is J2 by J1, okay? Everything is in units in this particular plot in which J1 is equal to 1, okay? But these are ratios. So without the Floquet engineering, you're going to probably be very close to 0 here. So as we computed, the ratio J2 by J1, so J2 by J1, was without any Floquet engineering of order TH by U to the power 2. This is significantly smaller than 1, significantly. So you're basically confined here in this orange part, that corresponds to the, for this triangular lattice, to this particular order, the 120 in AL order, okay? So you're basically, without the Floquet engineering, you're basically here, around 0 along the x-axis, okay? But then, with Floquet engineering, you can come all the way to these chiral phases and so on. This is, I can put the reference. This is something that I also collaborated during my postdoc, okay? How to come from here to explore all these regions here. It turns out that the most challenging ones to actually go to the green one. This chiral, as I told you, the circularly polarized light is very effective to produce chiral phases. But the question is, how can you increase J2 by J1 without breaking symmetries? So this chiral spin liquid does not have any lattice symmetry breaking, time reversal symmetry breaking, nothing. So how to Floquet engineering this green part? This is something that is non-trivial. This is what we did some years ago. I can show you a slide tomorrow with the results here, because you cannot break any symmetries, and the electric magnetic field will break some. The circularly polarized light will break mirrors and time reversal, and linearly polarized light will break some lattice symmetries. And elliptical polarization is even more complicated, because if you put some elliptical light here like this, it will be chiral, and it will break the lattice symmetries. Okay, it will break lattice symmetries. More questions? Okay, so this is what I had to show you. And again, tomorrow I can show a slide or two with some plots and so on. But this is the essence of what we had. So we are going to always find things like this. And clearly by choosing, so again, you choose this frequency and you choose A0, such that this ratio can be modified. Okay, this is the idea. You can even make this ratio to be equal to 0, for example. So what I typically do, I make plots as function of A0 for fixed omega. For fixed omega. So omega. And then you vary A0 in these Bessel functions. You have to add up all the Bessel functions. And then you can see what happens. Something interesting as well, coming only from this term, is that this coupling, let's say that we are plotting this ratio. So it starts at 1, because when A0 is equal to 0, you can check easily, then when A0 is 0, the only value of L possible is 0 as well, because all the other Bessel functions will vanish. So L is 0, and then you recover this ratio being equal to 1. Then you start playing this game, right? So this is the ratio of J1 Floquet divided by J1 stationary, and then you start and find something like this. So the only remarkable feature I would say about this plot is that it can change sign. So if you want to produce a ferromagnetic model out of an anti-ferromagnetic model, great. This already would do the job. This is the simplest thing that you can do. Even if you're not producing a spin liquid. So remember, I started this lecture by telling you about the square lattice with this anti-ferromagnetic order. I can all of a sudden have this Floquet engineering thing and have ferromagnetic order. Okay, this is already a change. It's a Floquet induced or time induced or out of equilibrium, let's say, in terms of Floquet modification. Okay, so just to revisit what we had in our first lecture. What we had in our first lecture, we had this so-called distance to equilibrium. And we had this plot as a function of time. And we had something like this, and then the Floquet plateau, and something like this. What I just proposed is that here you have anti-ferromagnetic order. Let's say that we are thinking of a square lattice. Now. So we had anti-ferromagnetic order. We start our Floquet engineering. We chose this particular value of A0 here. Okay, so we just go to a lab. You choose your intensity for this fixed value, and you choose your frequency accordingly. Don't make it to be too close to resonances. And then this is going to be a ferromagnetic state. Again, our point here is typically to find Floquet states that are very exciting. I wouldn't say the ferromagnetic state is the most exciting, but as a proof of principle, you can already see that you can change the phase of matter by doing this. And I will show plots tomorrow, telling you that this J2 by J1 and so on can be significantly enhanced safely, without going too close to resonances. That is always the tricky game, how to do it safely, okay? All right, I have some minutes left to start the second topic that I would like to cover in terms of strong correlations. And again, there are many things that I prepared that I will not be able to tell you. There are many, many different convenient ways of doing this calculation, because when you have a calculation that is this lengthy, it's good to have different ways of doing it. And one of them will come in this context of Kondo system that is called the Schrieffer-Wolff transformation, always convenient, almost always convenient to perform a Schrieffer-Wolff. It can help you a lot. But I will not have time to cover this for the Hubbard model. So, okay, so you can ask me during the coffee break, but I don't think we will have enough time for this at all. Okay, so for the Kondo systems, this is our second favorite strongly correlated system that we can study. And again, if you can tell me your favorite strongly correlated systems, and we can always discuss what would be the protocol. Okay, I started with probably my two favorite strongly correlated systems. So the second one is the Kondo model. Okay, so the Kondo model is number 2. The Kondo model, I will talk about it briefly, but I will come back to this tomorrow as well. The physics is sufficiently different that the Kondo model also deserves our attention for some minutes. Well, the basic idea is a model that Mr. Kondo proposed many decades ago, and Phil Anderson came with a way of showing that model was realized in this context of strongly correlated phases and systems, starting from what is now called the Anderson model. So the same way as we had this Hamiltonian, I didn't call the Hamiltonian by any name, but it's the Heisenberg model. We arrived at a Heisenberg model coming from a Hubbard model. Now we can derive the Kondo model. Our starting point that is completely analogous to the Hubbard model is the Anderson model. So the starting point is the Anderson model. And again, Anderson was sufficiently successful to have his name in so many models that there is ambiguity when we say Anderson model. Okay, there is condensed matter. There are some Andersons, but this one is the most famous Anderson. But there are several Anderson models from the same Anderson. Okay. All right, so the basic pictorial idea, I will not have that much time to do the algebra, but let me tell, as usual, let's solve the time-independent, let's motivate what is the time-independent model. We have to understand the time-independent model, otherwise there is not much hope. You take, and this is really pictorial, and this is from, I saw this picture, at least for the first time, in Pierce Coleman's book. But you take a local moment. So what is a local moment? You can think of this as a spin. You take we're going to call it local moment. And then you take your liquid. Here it's not as a quantum liquid, like the Fermi liquid. And then you put your local moment inside the Fermi liquid. Okay? The local moment inside the Fermi liquid. And then you want to know how this local moment, you can think of a local moment like a spin 1/2, let's say. A spin 1/2 coming from a factory that produces spins 1/2. In practice, this is going to come from D and F electrons, in which the charges degrees of freedom are frozen in a peculiar way, okay? So a local moment, and you put it inside here. What is going to happen to this local moment? So local moment, you can just think of this as a big arrow, as we often think of a big magnetic moment. So this local moment will now, okay, this is a bit too large. Okay, so the local moment is going to experience the neighborhood when inside the sea of electrons. So the electrons have spins. So what the electrons will do is they will become more or less polarized by this. The spin of the electrons will start interacting with this local moment. Okay? And this will give rise, and tomorrow I can tell you how. So far I'm telling you the result. This will give rise to this effective Hamiltonian, that is the Kondo Hamiltonian. And this is the microscopic origin. JK, J Kondo. Again, during this week we are writing many J's and many H's, okay? And many T's, but okay. J Kondo. Sum over K and K prime. It's simpler to write this in real space, to be honest, but let me just write it in momentum space for now. S of 0. So let's say that it's a local moment at the origin. So if you think of this not as a pictorial representation, but as a lattice, if you think of this as a lattice, what you have is the following. You have a lattice, and then here, let's say you put your local moment. So your local moment, blue, was here, in one particular site. And then you have, at the other side, you have electrons, the electron gas, basically, or the Fermi liquid. Okay, and the Fermi liquid is going to be at the other positions. And what this the other spins will do, they can move around. So these are, at these sites, you'll have electrons that can move around. They can move around. So in other words, this is a local moment inside a metal. So these other electrons can move around in such a way that they will try to screen this local moment. And this is the screening Hamiltonian. It's going to be an spin-spin interaction between this local moment that I'm choosing to be at the origin, so R is 0, scattering or trying to screen this, getting it screened by the other electrons. So the other electrons will be CK alpha, sigma alpha beta, CK prime beta. Okay, this is a dot product. So it's quite similar to what we had before with our Heisenberg Hamiltonian, except that this is a spin like we had for the Heisenberg Hamiltonian. We are calling it now local moment. And this is the spin density of conduction electrons. So it's a metal, so electrons move around. When you say electrons move around, what I mean by that is that it's a metal. That is a metal. And for a metal, you can write the spin density. So typically this is called big S, and this is called small s, but it's very hard to make this distinction. So this is, I'll try just to make it small like this, S of K prime. This is the spin due to the conduction electrons. Okay. I understand that in case you studied this extensively, like I don't know if you took a course that teaches this model extensively, this is a very brief introduction. It has very rich physics. So tomorrow for half an hour or maybe a bit more, I don't know, I will motivate why the interaction between this local moment and the conduction electrons take this form. This was done by Anderson, so you can find the Kondo model as the low energy model of this Anderson model. I'll do that tomorrow morning. And then we are going to do the Floquet engineering. Same ideas here. The main, already giving spoiler for tomorrow, the main finding is going to be that this, and I haven't defined this is called a single channel condom model. There is only one way in which the conduction electrons talk to this spin. It does in one very specific way. But it can be that you have two combinations here that are going to talk to this spin, two orthogonal combinations. We're going to define this better tomorrow. Two orthogonal, not symmetry-related combinations that can talk to the spin. And this is the two-channel condom model. And I will come back to this point tomorrow. But just so you can digest information during the day today, the same way as for the Hubbard model, I was looking for spin liquids. For this condom model, I'm looking for multi-channel condom lattices. Why? Because challenging to describe theoretically, not easy to find experimentally. Same motivation as for the spin liquids. This is the motivation here. So far, I don't have a condom lattice. I have a condom impurity. I'm taking this local moment and putting inside this liquid. And I only have one channel. So this is this is called the impurity case. So this is the impurity case. And this is one channel only. There is only one way in which the sea of conduction electrons that can move around is talking to this local moment. Tomorrow we are going to say that this could in principle have 2 or 3 or 4 different ways, and the physics is much more interesting when you have this multi-channel scenario, okay? Because then you have competing interactions. The idea always the same, competing interactions leading to interesting physics, and Floquet engineering helping that. This is the main thing in strongly correlated systems. Challenge, more energy scales. We're going to see this problem has 2 new energy scales that we're going to introduce tomorrow. Besides, we already have the U, we're going to have this epsilon F tomorrow, we're going to have the hybridization. More parameters that are related to the equilibrium model. So that's why the physics in equilibrium is already pretty rich, because you already have many knobs in equilibrium. But we are going to complement that with Floquet engineering tomorrow, okay? This is the last example, second and last example. We are going to continue that tomorrow. And tomorrow I also want to wrap up with some, I didn't have time to cover, of course, everything that I had initially in mind, but I will tell you a very personal view of what I find to be interesting in this field of Floquet engineering coming from the past 2, 3 years and so on, okay? I want to make specifically some comments about this quantum limit of light and about novel approaches related to that, okay? So questions? All right, if we don't have questions, I guess we have a coffee break now. Okay, all right, thank you.